and welcome to the worksheet 22 video key. All right, let's get started. We are talking about alkyne reactions, and this is part 1, worksheet 22. So we are going to start off with some nomenclature, and here are some rules for how to name alkynes, and we'll just go ahead and work through these examples. So we want to find the longest carbon chain. That includes the alkyne. In this case, there is only one carbon chain, so there's no substituents. We would want to number it to give the sp2 hybridized carbons the lowest number possible. So in this case, we could name this 1-hexyne or hex-1-ine. Okay, for this one, again, there's only one carbon chain. Because of the symmetry, it doesn't matter if you start on the left or the right. Either way, we get, again, hexyne, but in this case, we need to add that 3 to hex-3-ine. Over here, remember that we want the lowest numbers possible for the alkyne carbons, right? And that takes priority over halogen substituents. So we want the longest carbon chain, which is a 4-carbon chain. And all three of those fluorines, are substituents. So those get added before the parent. This becomes a 4-4-4 trifluoro. And then this is 4 carbons, so it's a butyne or a but-1-ine. Now, sometimes the 1 is left off, and if there is no number, it's implied that it's a number 1. But it's always, I think, more clear to just go ahead and add it. So here we want the longest carbon chain with the lowest number possible for the alkyne carbon. So we'll start over here. So we do have a substituent. It is a methyl group. So we have 6-methyl. And this is an oct-3-ine. And then we don't want to forget the stereochemistry. Because there's a chiral center, we do need to include that information in the name. So in terms of priority, this would be 1, 2, 3. So 1 to 2 to 3. The hydrogen pointed back. This is R. So we want to add that. Okay. Looks like they did this one for us, showing you how to name, do the stereochemistry in particular. Because we have both an alkene, which could either be labeled as E or trans, and a chiral center, which in this case is R. So there's 2 different ways you could do the stereochemistry. I would say probably the best way would be the first way that's listed here, right? 5E7R. The reason why you do E first and R second is only because of the numbering. So first 5 and then 7. And then 7-fluoro oct, because there's an alkene and an alkyne, the ene comes before the alkyne because of the alphabetical order. So we do 5-ene, 2-ine. Let's go ahead and practice that skill with this structure over here. So we want to number to give the lowest number possible for the alkyne carbons. We'd have 1, 2, 3, 4, 5, 6, 7. Substituents are just the fluoro group. Everything else is part of the parent. And this is going to have some stereochemistry. Between the chlorine and methyl, the chlorine takes priority. In this group in hydrogen, the carbon-based group takes priority. So this is actually a Z alkene. we would want to include that information. But there is no additional chirality, so we can just start with Z. And then we want to do 6-fluoro. Now we need it to be a heptene-ine, the appropriate locants in there. We can do hept, and then the ene, right? So this would be a 5-ene and 1-ine. All right, coming over here, now we have a diene and an ine. And we want, again, the lowest number possible for the alkyne carbons, because that group has priority. So 1, 2, 3, 4, 5, 6, 7, 8, 9. In terms of stereochemistry, we have 2 alkenes that have stereochemistry. This one is E. And then this one is priority here and there. So this would be E. And then the chiral center, which is going to be 1, 2, 3, but the hydrogen is pointing out at us, so this is S. We have a lot going on there, but we can just put that all in the front of the name. Start with, and just do number order, right? So 4, we always want the first number of the double bond. So 4Z, 6E, and then 8S for the stereochemistry. And now we want the rest of it. So what are the substituents? The bromo is a substituent, and then this methyl group is a substituent. So B comes before M alphabetically. We will do 8-bromo, 5-methyl. Okay, now this is going to be called, remember we talked about a diene-ine, right? So this is the 9 carbons is non, right? So non, 4, 6 diene, and 2-ine. Okay, let's go over some alcohol nomenclature as well. And so for the alcohol nomenclature, we want the lowest number possible for the OH group and the longest carbon chain. So 1, 2, 3, 4. So we do have a substituent and no stereochemistry that we need to worry about. So we'll go with 2-methyl. But we also have both an alkyne and an alcohol. It's going to become an enol. The all has to come at the end because it has the group that has the highest priority. So 2-methyl, we have bute, 3-ine, 1-all. All right. Next, we have a cyclic alcohol. The numbering starts with the carbon that has the OH group. Then we want the lowest number possible for other substituents. We would want to go this direction. The alkene is considered part of the parent. So this is not a cyclohexanol. This is a cyclohexenol. That's going to be an important part of the name. So what about the chiral centers? Right? That is important. And because it's in a 6-membered ring, it is known to be cis, so we don't have to include that information in the name. But we do need to include the RNS designation on the 2 chiral centers. In terms of priority, we have 1, 2, 3. Fourth priority group pointed back, so this is R. Here we have 1, 2, 3. And then we have fourth priority group again pointed back, so this is S. So we'll put that information to begin with. So 1R for S. Okay, then the rest of the name. We do have two substituents. Actually, we have more than two. We have two methyl substituents, so that becomes a dimethyl. And then we also have the bromine. So B comes before N, so we'll do that one first. So 4-bromo, 2,3-dimethyl. And then we have cyclo. We have the cyclohex. The cyclohexene, but we need to say cyclohexene. All right, let's look at the next one. So in terms of numbering, this one has, we want the lowest number possible for the priority group, which is the alcohol. So if we do 1, 2, 3, 4, that's not as little as 1, 2, 3. 1, 2, 3, 4, 5, 6. Look at chirality. So 1 to 2 to 3. Fourth priority pointed back. So this is S. And then 1, 2, 3. Fourth priority coming out at you. Right, so this is clockwise in R. All right, so for chirality, we have 2S, 3R. And we want to do substituents. So we have just the bromo group. 2-bromo. And then we start with the hex. 4-3-all. Oh, you know what? I totally forgot the stereochemistry of the double bond. This is a 4E. I should have that in there. Comma 4E. All right, looking at the last one, let's work. We want to have the lowest number possible for the alcohol. So 1, 2, 3, 4, 5, 6. So stereochemistry. We have a 1 chiral center right here. This will be 1 to 2 to 3. Fourth priority coming out at you. So clockwise becomes counterclockwise, and this is S. Whenever we have a double bond, we should think, is this E or Z? Stereochemistry wise, we want to start off with 2S. So substituents, we have a methyl and a chloro. C comes before M alphabetically. We'll do 2-chloro, 4-methyl. Now we have this is going to be fun. It's a hex E9-all, right? Ene comes before ine, alphabetically E before Y. And then the alcohol is the highest priority group, so it comes last. So we have hex. And then we have 3 ene, 5 ine, 1-all. Right. For more practice with nomenclature, practice with problems in the book. Let's go ahead and start looking at acidity. We talked about in lecture the fact that this proton attached to an sp hybridized carbon is fairly acidic, right? pKa of 25. However, it does, even though fairly acidic means it's acidic for a hydrocarbon, but not really acidic. So it does take a fairly strong base. Sodium hydroxide, as we saw in this example reaction, is not strong enough to deprotonate in terminal alkyne. And we showed that because using pKa values, equilibrium will lie towards the weaker acid, and 25 is a weaker acid than 16. Okay, so generally it's good to have pKa values, especially dealing with terminal alkynes, because sometimes, like in the second case here, it actually will go against ARIO. So we really need to use pKa values because we'll have conflicting directions based on whether or not we're considering the atom, resonance, induction, or orbital. Okay, so first we're going to, it says draw the curved arrows, right? Predict the products. Let's do that first. So we'll do, this is our base, proton transfer. So we need to go in and draw in the products. So we have HF. And it's going to be the same alkanite ion in all cases. The only thing that's going to change is the conjugate acid. Go ahead and draw this in. Again, you don't have to draw in these C's. Sometimes it's useful for alkynes, but you don't have to draw them in, and they won't always be drawn in. Okay, so what we want to know are what are the pKa values, right? Because we know the pKa of the acid is 25. So what is the pKa of the conjugate acid? That will allow us to know which way the equilibrium lies. So the pKa of HF is about 4, approximately. pKa of ammonia is about 38. pKa of H2 is about 35. pKa of methane is about 50. So you could have looked those up in chapter 3 or just Googled it. Okay, so in which way will the equilibrium then lie, right? So basically, if we want to favor the reactant, the products, we need to have a larger pKa value, 25, right? So that this is the weaker acid. So these ones here are larger than 25, so those will favor reactants. So these are strong enough bases to deprotonate the terminal alkyne. So is this one, by the way, at 50, definitely strong enough. But this one, the equilibrium will lie here. 4 is definitely a lower number than 25. This is not considered a strong enough base to deprotonate the alkyne. Right, so that is good to know. Moving on. So it says fill in the empty boxes with the proper structures or reagents. Okay, so we want to choose one of those bases that's strong enough to deprotonate a terminal alkyne. So in lecture, I told you that sodium amide is definitely the most common one. However, you could have written sodium hydride or butyl lithium, for example. Those are also other options based on the analysis we just did higher up on the page. And then if you treat this with a unhindered alkyl halide, it can come in and do an SN2 reaction. What we'll end up with is adding these 3 carbons. So hold it, right? 1, 2, 3. And the byproduct would be sodium bromide. So here, though, unfortunately, this is secondary alkyl halide. So this is going to favor E2 over SN2. So as a result, it will do E2. And the mechanism for that, this is considered a non-bulky base, so it will likely take the more hindered proton to get the more stable, more substituted alkene. So you can think of it like this, or you could flip it. Right? And what's more likely? I think it's more likely that it would go through this coplanar arrangement. Remember that E2 requires the anti-periplanar arrangement. So we would draw in our base and the likely E2 to form the more stable Zaitsev and trans alkene. So no, Zaitsev. Okay. Moving on to the next page, preparation of alkynes. So recall that we can take either a geminal dihalide or a vicinal dihalide and do a series of E2 elimination reactions to get a alkyne. So let's go ahead and use that information to fill in the empty boxes here. So to go from an alkene to an alkyl halide, we need to do radical halogenation. And the conditions for that are Br2 and either heat or light. And then to go from the alkyl halide to an alkene, we need to do an elimination reaction. This is a Zaitsev elimination. So we'll do E2, and we'll use a small base, like sodium hydroxide, sodium methoxide, or sodium F oxide. We'll do E2, Zaitsev. Next, we want to do an addition reaction to go from the alkene to the alkyl halide. We want to add H and bromine, so HBr across the double bond. And we want it to go anti-Markovnikov. Recall that if we add HBr with peroxides, we can do anti-Markovnikov hydrohalogenation. All right. Oops. And then we want to do another elimination, but in this case, we want it to be Hoffman. Right? So E2 Hoffman. So that requires the now we want to do an addition reaction where we add 2 bromines across the double bond. So that's just going to utilize Br2, right? And then that is an alkene addition reaction, right? We call that halogenation or bromination. This technically is a chiral center, but we don't really mention it because we're about to get rid of it anyway. Next, we want to do a double E2. 2 times E2, right, to form the elimination. So we actually need to use excess NaNH2 followed by water. Remember that we have 2 equivalents go towards the E2 reactions, and the third equivalent deprotonates the terminal alkyne, and the water reprotonates. And now we want to do a alkylation, right, of the terminal alkyne. Ran out of space. Round up here. And so that's a reaction from this chapter as well. So we want to use just 1 equivalent of NaNH2 to deprotonate that. And then followed by, we're just adding a methyl group, so methyl iodide. Okay. Let's practice some more multi-step synthesis. So we can work backwards or we can work in the forward direction. So you can practice doing whatever suits you. And we can kind of also work at it from both directions. Sometimes that's helpful as well. So starting from an alkane, right, there's only one reaction you can do, and that is a radical halogenation. So we'll go ahead and add Br2 and light, and that bromine will go on the most substituted position. From there, we need to eliminate. We want to get the elimination so that we can do an addition reaction to get to the final product. So to do elimination, all three beta carbons are the same, so we don't need to worry about regioselectivity. So even sodium hydroxide work well here to do E2. And then the addition reaction. So what are we adding across the double bond? We're adding H and OH. We want this to go anti-Markovnikov. Anti-Markovnikov. And we call this a hydration because we are adding H and OH, which together is water. So how do we do an anti-Markovnikov hydration? Well, we can do, you have to remember these reagents, right? So if these are not coming to you quickly, then you need to do more studying of the reactions. So for this, we want to do hydroboration oxidation. We start with BH3THF, right? And followed by sodium hydroxide and hydrogen peroxide. All right, for this one, we want to convert this alkane into an alkyne. So again, starting from an alkane, and we're not really doing anything to the aromatic ring, so don't worry about that. You have to do a radical halogenation. So we have to, and it would actually be useful to go ahead and add 2 halogens on so that we can do a double elimination to get the alkyne. This is a radical reaction, but because we're adding the radicals at the benzylic position, we will use NBS. Right? And we're going to use excess to make sure it adds both available, or replaces both hydrogens at the benzylic position. So from there, we can do our double elimination process. So the first step would be excess sodium mid, followed by water. Remember that we'll do a double E2, deprotonate the terminal alkyne, and then reprotonate it in this. All right, continuing on with reactions of alkynes, we're going to look at reduction. So if we want to reduce an alkyne all the way down to alkane, we want to add in hydrogen gas with a metal catalyst, such as platinum or palladium on carbon. The hydrogen gas is always in excess, so it gets added twice. The first equivalent produces a cis alkene, and then it gets further reduced all the way down to the alkane. If we want to stop at the trans diol, then we can use dissolving metal reduction conditions. Sodium metal in liquid ammonia. That will do a radical reaction where sodium metal adds electrons. And then the protons come from ammonia. So it's going to preferably go through this intermediate such that we get the hydrogens adding anti, or to give a trans product. To get syn reduction, in order to get the cis product, we use hydrogen gas and a poison catalyst, such as Lindmer's catalyst. So it says in the mechanism for the anti-reduction of alkynes, only B instead of A gets protonated to the anti-hydrogenated product. Explain why. So it's more stable trans the product formed from lower okay, to less steric hindrance. Right, these methyl groups opposite one another, definitely going to be less sterically hindered. Okay, moving on. Fill in the empty boxes with the proper structures or reagents. This is just a reduction of an alkyne to an alkene. So we just want to use hydrogen gas and catalysts like platinum or palladium on carbon. Here we're using hydrogen gas and Lindlar's catalyst. This is going to give us a cis alkene. So we can draw the alkene cis. 3 and 4, 5, 6. And then if we had used sodium, metal, and liquid ammonia, we would have gotten trans alkene. Okay, and then from there, we want to draw the syn dihydroxylation. So recall that osmium tetroxide does syn dihydroxylation. So the easiest way to draw that is just to draw the carbon skeleton. So I'm just going to use model 2, but you can also use model 1 to draw the product. So for model 2, we just leave the carbon skeleton where it is. So kind of start with the different carbon skeletons. And then I go ahead and make sure that draw the OH groups, either both on a dash or both on a wedge. Great switches. Okay, so, and remember that this is not the same as this, because if you wanted to get it in this configuration, you'd have to flip this over, and then it would look like it. Right, so this would be plus. So I drew this through using model 2. Okay, so more synthesis. And in this case, it looks like we are going to be adding more carbons in some cases, right? So ask yourself when you're doing these, are the number of carbons the same? If yes, I think we forgot the word don't, right? We don't need to use an alkanite ion. And if not, if it's no, then we do need to use an alkanite ion in order to make a new carbon-carbon bond. And then how do we get the right functional groups in the target? So from here, we're starting with an alkane. So starting with an alkane, we only have one choice. We have to do radical halogenation. And even though we want the bromine to be on this carbon, it's going to go on the most substituted carbon. Now we have to do a little beam of moving it to the right carbon through a series of elimination addition reactions. So we can eliminate it and then add it back in the right place. So radical halogenation, we go to enlight. This is a Hofmann elimination. We need the bulky base. And then we want to add in H and Br across the double bond, and we want it to go anti-Markov. We're going to do HBr with peroxide. In this case, we definitely do not have the same number of carbons. So first we want to convert the alkene to an alkyne, then we want to add more carbons. So we need to go through an alkanite ion to do that. So looking at that, we will do first go here and then go here. Right? So in order to convert an alkene to an alkyne, it's a two-step process. First, we do a halogenation reaction. And then we do a double elimination to get the alkyne. And then from the alkyne, we can do an alkylation. We have ER2 followed by excess sodium amide, followed by water. And alkylation, one equivalent of sodium amide, and we're adding an ethyl group in this case, so ethyl iodide or bromide would be just fine. So we definitely look at how much you need to know these reactions to be able to do these type of problems. All right, for the next one, are we adding any carbons? Nope, we have 7 carbons here and 7 carbons there. So we're just manipulating the functional groups. Starting from an alkane, there's only one radical halogenation, and the bromine will go on the most substituted carbon. From there, we can eliminate it. And then we need to do an addition reaction. And then we can do another elimination. And then from here, it's actually only one step. So get rid of this, right? Get there directly. Okay, let's go ahead and add in the reagents. So to do radical halogenation, we have Br2 followed by an elimination. All of the beta carbons are the same here, so we don't really need to worry about Zaitsev versus Hoffman. Just use a small base. From here, we want to add H and Br across the double bond, and we wanted that to go anti-Markovnikov. So add those peroxides. To get the Hoffman elimination product, we're going to use a both base. And then from here to here is just one single addition reaction. We're doing a hydration because we are adding OH and H across the double bond. It is going anti-Markovnikov. Anti-Markovnikov hydration is hydroboration oxidation. Look at the next one. So we're definitely changing the carbon skeleton. We're going from 5 carbons to 6. So we need to get a terminal alkyne. So there's no fast way of just adding 1 carbon. Unfortunately, we have to work really hard to do that. We start with radical halogenation because that's the only choice available to us. We can do an elimination. Followed by an addition reaction. Followed by another elimination. Now we're getting closer to what we want. The goal is to convert this alkene in a 2-step process to an alkyne. And then we can reduce the alkyne to drawing in our reagents here, starting with Br2 and light, doing a Zaitsev elimination, followed by addition of HBr anti-Markovnikov, Doing another elimination, this time Hofmann, the bulky base. Adding bromine across the double bond, only to eliminate it. And then reduce it using hydrogenation. Okay, more practice with synthesis. So we're definitely changing the carbon skeleton here. So we want to get to a terminal alkyne that we can alkylate. Luckily, we have an alkene. We can do a two-step process to convert that alkene to an alkyne. Remember, we don't bend alkynes, so we want to go linearly with that. And then we want to alkylate. Get 2 more carbons on there. So Br2 followed by excess NH2, and an aqueous workup followed by alkylation, which is just one equivalent, strong base, followed by, in this case, ethyl iodide or bromide to get the additional 2 carbons on there. Here again, we need to go through the same sort of process because we want to add carbon. So it's actually the same starting material, and we can get to the same sort of alkyne, and then we can actually just continue on with this to get this. So I'll just write same as above. Okay. Until we get to this point. We have the alkyne. Now, how can we do this? Well, we want to first reduce to a double bond and then reduce D2 instead of H2 to get to the product. So the tricky part here is recognizing that you can get these 2 on because D2, right, is synthetically equivalent to H2. So we need to do a hydrogenation. However, hydrogenations give syn addition. And that looks like anti-addition, right, with the 2 opposites. One thing that we could recognize here is that this would be equivalent to drawing it a different way. If I just flip this part over, I'm going to get here. This is actually a meso compound. So what that shows me is that this would be syn addition if this was a cis alkene. Right? So I am going to target actually the formation of a cis alkene. So I want to do alkene, the 2 ethyl groups attached to them. Right? We want to make sure that this cis. And then I can do hydrogenation. And that will also go through syn addition. So this one is a bit of a tricky one. So we want to do H2 in Lindlar's catalyst. And then we want to add B2 and platinum or palladium on carbon. Okay. Let's do some more synthesis. So fill in the empty boxes with the proper structures. We want to add in bromine. Then we're doing that double elimination. That will give us the alkanite ion. linearly draw. And because it didn't say water, it's going to stop at this point. I guess maybe they intended to say water because it might have been an accident. I intended to say water. Get rid of that. So it's just a terminal alkyne. And then with sodium hydride and ethyl bromide, we'll be adding an ethyl group. So Lindlar's catalyst would reduce this to a cis alkene. I like to just draw it like this and then go here. Make sure that these are on the same side. And this would have given a trans alkene. A little easier to draw. And then, so notice that these conditions do anti-dihydroxylation. Right? And these conditions do syn dihydroxylation. So it worked out that if you start with a cis alkene and do anti-dihydroxylation, you get the same product as if you start with a trans alkene and do syn dihydroxylation. So there's a bunch of different ways you could potentially draw this, but maybe just starting with this one and adding in the two groups syn. All right, so then it says explain why the final steps give the same product. So let's go ahead and do that. So if we look at the cis alkene, so we have and we do anti-dihydroxylation. What we'll see is that we're going to get, using model 2 again. So I'm just going to draw it the same way that I see the carbon skeleton here. And then I'm going to add in the OH groups anti to each other. So one goes up, one goes down. Right? And then what I can do is rotate around that double bond. And so this is equivalent to what we drew up here. Okay, so that's why it's the same. So anti-dihydroxylation of cis alkene would produce the same as syn dihydroxylation of a trans alkene. All right, we are done today. Have a good